have several applications of that. We have different kinds of tasks, supervised learning. We will focus on that, but we will also see things about supervised learning. Finally, there are other kinds of learning, reinforcement learning. Okay, so yeah, we saw that usually data mining process, the use of machine learning techniques, follow cycles where first we have to define the goals of the data mining technique, the problem that we want to solve, then the collection of the data, pre-processing, and everything. Then this is where we will focus on the creation of models that explain the data and predict things, and later interpret the results and apply them and deploy them in real life. And this is a cycle where well, you can go back at any step because you find that the results that you have found or obtained are not good enough, or you want to change something. Well, so this is something that we saw. This is also what we explained. The data should be in tabular form, where each row represents the objects, instances, or examples of the thing that we want to predict. That each of the columns represents features that describes each of the objects. In this case, we have flower. Each row is a flower, and the columns describe the flower thing, which is the sepal length, with length, petal length, and width. Also, we have an special column that is the thing that we want to predict in general for this kind of elements, in this case for flowers, okay? Depending on the sepal length, with petal length, and with the kind of species, okay, that flower represents or belongs to. Okay, so we have this information on tables, and we also saw that that we have to do a lot of pre-processing on your table, usually because the data that you get from your company is or your organization where you apply data mining, usually is data that is not clean enough. It has redundancies, errors. We have problems with formatting data. We have missing data in some cases, and yeah, we have to solve all this problem. Okay. But once we have cleared the set, then that is what we will do now. We will focus on is in the creation of models. Okay, that tries to predict the thing that we want to predict. So in data mining, we have we use machine learning algorithms to create the models, and we will focus on that, on how we will create these models. Okay, models can be of different kinds depending on the assumptions that you take about the thing that you want to predict, and yeah, it can return something like a class or a real number. If we do, in the first class, we are talking of models for classification, in case that we predict a real number from the data. Okay, D is the number of descriptors, that means columns that you have, so that means that you have an input point or case, and you want to know the class. Okay, that means that the model is this function that says, hey, this element belongs to this term. Okay. In the case of regression, where we don't want to classify things, we want to predict a number, for instance, the price of a house or whatever, according to different properties that describe the houses, like the number of rooms, the square meters, and so on. So yeah, we are talking of a model that will try to predict the price, in this case of the house, and this is a regression, a model for regression, okay, when we try to predict analysis, okay. Then models can be functions, okay, like this, where the output is exactly the thing that we want to predict, and in other cases we have models that predict probabilities, okay, this is the probability These are discriminative models, and these are generative models. Generative models are able to modelize the probability of joint probability of data and the label of the data. And in the case of discriminative models, you have the probability of a label given that you have this data. Okay, so this is discriminative because it says if you belong to this class or this other class, and here you have generative models because they build this estimation of the joint probability of the distribution of the data. Okay, with this information, with this probability, you can take a classification and so on. Okay, so for instance, in the case of discriminative models, where we have two variables and the variable of two possible classes, okay, two possible answers or values for the y, then it's if you have a discriminative model, it's easy to know which is the class that corresponds to a given data. Okay, is the class that maximizes this probability, and this is pretty obvious. So with this information, you can do the same things that we do with models as functions. But here we have a lot more information, and we can do a lot more things. Okay. So yeah, and so we ended here.
What does stochastic mean?
The
Stochastic? Yeah, stochastic process.
Okay, and the stochastic process is a process where we have randomness in some way. Okay, so this is when you are evaluating probability distribution, you are assuming that your data, okay, uses this stochastic, has this stochastic property. So we will see more about this later. Okay, so yeah, about learning. So the idea is, okay, we know what the model is. It can be a function or an estimation of probabilities, and that are, with that information, we're able to predict the label in the case of classification, or the value in case of regression, predicting this value for incoming data that you want to know these values. Okay, so what we do in machine learning is, okay, instead of building or programming, doing a program that says, okay, under this circumstance, if somebody fulfills all these properties, then it belongs to this class. The thing that we do is to learn automatically from a set of examples, okay, these, how to assign these labels to the class. Okay, this is what we mean by learning. And learning means obtaining a model, okay, a model of the kind that we have seen in the previous slide, that predicts well unseen data. Okay, this unseen data is something that I want to stress, because in machine learning we have two kinds of data: the training data and the validation data. The training data is the data that we use to train the model, okay? And the validation data is data that has not been used for training, okay? It's new data from the point of view of the model. The model has never seen before that data. So that's what we say unseen data. And we want is a model that predicts things for unseen data, okay? And let's see, it's very easy to understand this. For instance, let's think about data mining process where you have, you are, for instance, you are the owner of a bank, okay? And in that bank you have different customers, and some of them ask you for a loan and money that they have to return after some time. Okay, in this case, maybe one interesting thing that you can do is to build a model that tries to predict if somebody will return the loan or not, if will return the money, in order to accept this loan for the customer. Okay. So we want this model, so in order to build this model, we will use historic data about the bank. Okay, the bank has several customers that previously asked for a loan, and some of them returned the loan, some of them not. Okay, so with this data, we will try, this will be my training data, and with my data, this data, I will train a model. Well, the thing is that I want a model that works well on unseen data. That means not for the customers that previously asked for a loan in the bank, okay? Because I know that, okay, if somebody didn't return the loan, I will never give him again another loan. So this is not useful. What's useful is when a new guy comes into the bank and asks you for a loan. This is an unseen case, okay? This is somebody that has not been in the never in the training data set, and yet we want to predict something. We want to give the predict if that guy will return or not the loan with high precision. Okay, this is the idea. Okay, so it has to work well for unseen data. But yeah, then we have this question: how learning is possible at all? Okay, so for instance, let's assume that we have 4 cases of a series, and this will be my training data. And from this training data, I have to build a model that describes which is the next number of this series. Okay, so if I ask you a number, probably you will say 10. Okay, why? 2, 4, 6, 8, 10. You are adding 2 to each number, so probably the next one is 10. And that's true, this is a possible explanation. One answer is 10, okay, and the model is this function that says 2 multiplied by n, where n is the order, the number of the series, okay, the index of the number of the series. But we also have this possible answer 152 that belongs, that is explained by this other model, okay? Both models are consistent with the training data set, okay? Both models explain perfectly well the training data set, but they predict different numbers, okay? So they have a different behavior, and yeah, probably if I ask you which is the most probably answer, you would say 10 is probably the most probable answer, okay? Because yeah, we have some bias in our lives towards simplicity, okay? That means that yeah, if somebody has to predict which is the next number, he will not build a model like this first. He will try to build a model like this one that is simpler, and probably is the answer that you will give me for this set. Okay, so the problem is that from the mathematical point of view, the learning problem is ill-defined. Okay, it has infinite solutions. Okay, in particular, you can. This is a solution, and this is another one, and I can give you an infinite number of different possible solutions for this problem. Okay, and the problem is that each of them will return for unseen data, okay, for the next element that has not been used in the training that is a different answer, okay? So how can we decide which is the model that is right in this case? Well, one option is to obtain more data, okay? If we get more data, okay, a lot more data, then there are some, and this data is 10, 12, 14, and so on. So this data will some way give more weight to this possible model and get rule out the other one, because this model does not explain this one. Okay, so this is something that we can do. We can get more data, but still the problem is there. Okay, why? Because if I'm using this training data again, I can give you infinite solutions for the next infinite model that explains the next number. Okay, So this is not really solution. So what we will apply in machine learning always is a criteria that says when you have different models, usually the simpler that explains your data, okay, that fits, that explains your training data, usually the simpler one is the one that generalizes better to unseen data. Okay, this is the principle of generalization that is also known in science as the Occam razor or the simplicity. The idea is that when you have different explanations for something, take the simpler explanation because that is consistent with the data, because this is probably the right model. Okay? And in fact, mathematically we can prove that there are proofs in the space of logics, okay, and logical formulas, that when you have a training data set that contains different values for different a training data set that you want to learn a logical function from a given data set that shows some properties and it has some rocks or a table, we can prove that the simpler models are probably have more probability of being the true model behind the logical function that we are representing in the data. Okay. However, don't care about this. The idea is that we will use these Occam razor criteria in order to simplify, to use or go towards a simple models. Okay. So how can we obtain simple models? There are different ways to do this. One is reduce the hypothesis space. That means that I will not consider all possible functions that explain my function. I will only consider linear and quadratic maybe formulas. In this case, this one formula, this one function will be ruled out because it has power to 4 terms, so it's not quadratic or less model. Okay. Why? Because we can agree that this model is a lot more complex than this other one. Okay, so if we go towards simplicity, we will select this model over this other one. So this is called the inductive bias. Okay, you see there are inductive bias, the title of the slide, that's what it means. Okay, I will introduce some bias, okay, because if we don't do that, this problem is not well defined, the problem of learning. So we will try to reduce the space of possible models, okay, and I will look into a smaller one in order to avoid this infinite number of models. Another possibility is to use regularization. That means that you will consider all possible models, but you will add a penalty that penalizes formulas that are, or functions that are more complex. Okay? For instance, considering the number of terms that we have in our function, or the sum of the parameters of this equation that are the coefficients, in this case of the polynomials. Okay, we will see in detail these two techniques because this is important. It's something that we usually do in machine learning. Okay, so the idea is, again, this machine learning problem is not well defined. It has infinite solutions. We will add something in order to reduce the number of infinite solutions to something that makes sense. And in this case, the thing that we do is to add a constraint or that says, okay, of all possible models, I will select the one that is simpler. Okay, this is what we will do. Okay, we will see this later in more detail from the mathematical point of view. So the idea, we know this is this is not a formula, but we can consider that from intuitively that the true error, that means the error that you do in your in unseen data, okay, the generalization error, the error that your model will do on data that has never been used for the training from new data. Can be decomposed in these two parts. The first one is the training error. That means how your model explains your training data. Okay, if your model does not explain perfectly your data, probably it will not neither explain data that has not been seen before. Okay, so this is one part of the error, and the other one is the complexity of the model. Okay, the more complex the model, the more error we will have on the unseen data. Okay, generalization error. Okay, so we will see some examples of this later, but first let me introduce some definitions that are important. Okay, so yeah, we say that we want to predict labels. Okay, and we have said also that we have a measure of the errors. Okay, that the model do on that. Okay, so let's formalize a little more all these things. Okay, so we will assume that our data set is a set of points. Okay, where each of these tuples consists, this is a vector in this case, with all the properties of your data set. That means a row of your data set, and this is the corresponding label to that row in your data set. That's why it's a vector, and it's in this bold term. Okay, so this will be usually in bold vectors, and in these italic values are represented as scalars or labels. Okay, in the case of classification. Okay, so this is our data set. So we will also say that if we have a model F, Y, okay, with this height here, is the prediction that our model will do for this case. Okay, so we have the true label, we have the predicted label for that case. Okay, this is the prediction. And then, in order to measure the goodness of our model, we have to define this error function or loss function. Okay, this error function, the thing that it does is to compare the true label and the predicted label, okay, and measures how different are the predicted values of with respect to the true values. Okay, if they are exactly the same, usually the loss is zero because you have got a perfect match. Okay, in the case of classification, usually it depends on how you define the loss function. In the case of classification, if you say the true class, the predicted class is exactly the true class to which the point belongs to, then we have a loss of 0. In case that they are different, maybe you have a loss of 1. Okay, and okay, so this is my loss function. And then the generalization error, this is right here in the form of an integral, but yeah, it's exactly the same that I'm doing. And in addition, this is the expectation of the loss function for data selected from the true population, okay, not from the training data set. That means that this data that is used to compute the expectation is unseen data. Okay, and this is the true error, okay, the true error of the model, okay, where true means generalization errors, how your model works with data that has not been seen before, okay. This expectation can be computed in this way. Usually we cannot compute this integral because we don't know these parameters of probability and so on, but it can be computed in this way. This is what we call the empirical error. error. The empirical error is an approximation to the true error. And the thing that we do is to, instead of consider all possible examples in this integral, we will randomly select some of them. Okay, we will select, I don't know, maybe 1,000 or 10,000 or 1 million, whatever, examples. And then I will compute the loss function for these 1,000 examples that were not used in the training. Okay, these are new data. And then I will do the average of the loss function. Okay, and this is the empirical error. Okay, this is the true error, but usually the true error cannot be computed. So the thing that we have to do is to compute the error empirically, the error of the function of the model empirically, doing this sampling of the data and approximating the expectation with the mean of the loss, okay, for all this data that I'm using to compute the empirical error. Okay, yeah?
Does the idea that true error can't be calculated only apply if you're using a regression model? Because if you're doing something that's categorical, you don't know exactly.
So it depends on how you define the loss function. The loss function it has been defined today or now. I have defined the loss function for a classification problem where you are comparing one label with the predicted label with the true label. But in cases where you have a regression problem, okay, then you can do something like the square difference between the predicted, that is the square errors, okay? So this is something that you have to choose for your problem, okay? And depending how you do things, then the errors are differently considered and so on. But you have the freedom to choose your loss function for your problem. Okay? So, and the thing that we want to do is, okay, we want to minimize this true error. We cannot do this because we cannot compute this analytically. So what we have to do is to select some data randomly, compute this expectation of the error, the empirical error, and then try to reduce this as maximum. So the thing that I will try is to find a function that minimizes this loss, okay, for my data. Okay, this is the this criteria to learn, okay, I will learn this function. This criteria is called empirical risk minimization. Okay, this is what we do. And this is the fancy name that we use in machine learning for minimizing the empirical error. Okay. So good. But we know, and this is something that we have said before, we know that when you have a training data set, maybe there are infinite solutions, different models that explains perfectly well your data. So there can be a lot of models that explain with the same empirical error. Okay, so what we will do? What we will do is just to decide between one model or another one. The thing that we will do is to penalize those models that are more complex. Okay? And how we do that? Well, then instead of minimizing the empirical error that can, if we do this, we can obtain in some cases functions that are too complex, and then we know that these functions that are too complex will not generalize well to the same data. Instead of minimizing this empirical error, the thing that we will do is to minimize this regularized error. Okay? The regularized error has two parts. The first one is the empirical error, as always, as said before. Okay? But now we will add this term. This term is a penalty that we add, that we have a value that depends on the complexity of the function. This cardinal of f represents some way, this is an abstraction, that is something, it's an operator that computes which is the complexity of the model, measures the complexity of the model. Okay? So what you are doing is, okay, I want to minimize these two things, the complexity of the model and also the error. Okay? So I want to do both things at the same time. Okay. So this, of course, you cannot minimize both things to 0. Okay? Usually this does not exist. So there is there is a tension, okay, between the minimization of this term and the complexity of the function. Okay. So sometimes you will have functions that are more simple and that have higher empirical error, and some other functions that are less are more complex that have lower empirical error. In both cases, both values have exactly the same regularization error. Okay, so one term can be high, can be other low, and so on. So in order to balance or this trade-off between the complexity of the model and the error on the data of the function, we have this lambda parameter. This lambda parameter is a parameter that it's a hyperparameter, in fact, okay, that has to be chosen, okay, for your problem. Okay, and we will see later how to adjust this parameter. Okay, but yeah, the thing that I want to stress here is that sometimes we will not only minimize this, we will try to minimize the error plus the complexity of the function. And this is done adding to the thing that we want to minimize, this term, that is this penalty term that penalizes the complexity of the model that we are using to do the prediction. Okay? So, okay. We will see that in the next set of slides in this. So, let's put an example just to understand what is happening. Okay, the things that I have explained. Okay, so yes, in here we have a regression problem. Okay, in this regression problem, the loss will be the difference between the predicted value and the true value. The function that we want to that it's behind the data is these orange dots, okay, this sinus function, okay? And then from this sinusoidal function, we extract the training data set, okay? The extraction of the training data set that we will use to train models are represented with these blue crosses here, okay? You can see that these blue crosses are not on the sinus equation and the sinus curve, and that's because usually when you're measuring something, there is an associated error usually. Okay, so let's assume that yeah, this is my training data that in fact corresponds to this, but well, in the measuring of the data we have these noisy measures, and then we have this. So my training data are these crosses, blue crosses, okay, that are examples of the true sinus function that I want to learn. And the thing that I will use to learn this are polynomials. Okay, so my models will be different polynomials. Okay, polynomials can have different degrees. That is the degree of the term of the equation that has a higher degree. Okay, so in the case that you are using a degree equal to 1, that means that you're trying to predict your data with a straight line. Okay, you're doing linear regression. And yeah, in this case, this is the best for the training data. This is the best thing that you can do. So that means that you are using all these blue dots to learn a line that minimizes the error, okay? That minimizes the distance of the predictions with respect to to the true values. Okay, this is what we have. So yeah, this is for polynomials of degree 1. For polynomials of degree 2, that means that you have a parabola, okay? And then this is the equation that, well, if you try to fit with a quadratic formula model your data, this is the best expression that you can find. With the model of degree 3, this is the equation, this is the curve that you learn, with a degree equal to 8, 15, and 25. Okay? So, notice something that happens. These are the most extreme cases. This is the simplest one. This is the model that is more complex. Okay? The idea is that if you look to this formula, you will see that the function passes very close to the training points. Okay? So we have a model that explains very well the training data. Okay? Very well. And this model does not explain well the training data because the error for this point is very large, for this point is very large, and so on. Okay. So one thing that we can do is to picture a graph like this. In this in this graph, the thing that we have is on the x-axis the best of the models with a degree 1, 2, 3, 4, 5, 6, 7, and so on, up to 25. So this is something that we will reproduce next day with some notebooks in Python. Okay, so this is something that you can run if you want. Okay. So the curves that you see here are the two different errors, what we call the training error and what we call the generalization error. Okay? The training error is this blue line that you see here, and it simply adds for all the training data set, that means for all the blue points, the difference squared between the true value, okay, and the value according to the model. Okay? And the thing that you will see is that for the two first models, degree 1 and 2, the errors, the training error, that is this blue line, is very large. Okay? Yeah, it's something that we can observe here. Okay, the sum of all these distances squared is very large. On the contrary, on the degree 25, what we can see is that the differences between the predicted values and the training data set is very small. Okay? So that's why we see this decreasing curve that says, hey, at the beginning I have a lot of training error, and later the degree or the complexity of the model grows, then this training error decreases. Okay? And you could say, cool, okay, the thing that I want is to reduce the error, but what I want to reduce is not the training error. Okay? What I want to reduce is the generalization error. Generalization error means errors for data that has not been used for training the model. Okay? And how we do this data? Here. So the thing is that we know points that belong to this curve that are the orange points. So we will compute the error on the orange points. Okay, and this is the second equation, the second curve that we have here. Okay? And you will see that, well, for models 1 or 2, yeah, this error is large, but for here, for these models 3 to 8, these errors are smaller. Okay, notice that these lines almost passes over the orange line. Okay, but if we increase the number of or the degree of the polynomial that we are using, in the case of degree 25, notice that, this curve do a lot of weird things, okay? And the difference between these points, for instance, and the prediction is very large. And this is what we see here, okay? As you grow the complexity of the model that tries to explain your data, the error on unseen data, this generalization error, grows, okay? Why? Because, you are trying to explain so well your training data that you are not fitting well, okay? You're trying to predict particularities, even the errors in the measurements of the data, and then you are losing the generalization ability to other files, okay? So clearly this is a too complex function, okay? That does not work well. These are two basic models, okay? The right model is in the middle, okay? Something like this, okay? Well, this is a curve that usually has this form, and it's common not only to polynomials, but to any kind of model that we use. As the complexity of the model grows, okay, the thing that we observe is that the training error decreases even more, okay, but the validation error decreases, but at some point it starts to increase, okay? When we are in this regime, that means that we are underfitting, we are not doing well, we are underfitting our data. Okay, and this is what happens here. We are not explaining the training data set. Okay. Okay. As you explain your training data, you also generalize the things to the unseen data. Okay, to this data that has not been used to train the model. At some point, and then when you arrive at some point, then increasing the complexity, what it does, what happens, what it provokes is that this error on unseen data it starts to grow. Okay, and then in this case we have a name for this regime that is overfitting. Okay, overfitting means that you are fitting so well your training data set that you try even to explain some things that cannot be explained by the model because they are errors. For instance, maybe notice that these measurements of the process are contain some errors. Okay, and the model tries to explain even this error that has no explanation because it's a problem about the measurements. Okay, so in this case we have overfitting, in this case we have underfitting, and this is the sweet point that we have to find. Okay, this is the thing that we want to obtain. This is the best model here, okay, because this is the model that has less error on generalization, okay, on data that has not been used as for the training. And this is an illustration of this, okay, so the model that we should select is someone in this range, okay, from 4, 5, 6, 7, or so on, okay? Okay. So something that we can do is, train several models and try to find this one that, we have here this equation, okay, the true error, the generalization of the error, it has two parts. On one part is the training error, the error that you do to explain the training data set, and on the other side you have the complexity of the function. If the function is too complex, then you go overfit. Okay, if this is very large, then you are doing overfitting. If this is very large, that means that you are doing underfitting. Okay, and the idea is to take something where both things are as low as possible. Okay, this is the idea.
One question about this is
Yeah,
why the minus rainfall?
yeah. This is a bound, an upper bound for the true error. Okay. However, don't take this equation as a true equation. Okay, it's a description of what's happening. Okay. Okay. Another way so we can do this. Okay, we can try different models and test the different models on different data that has not been used for training, validation data, and then find the best one. Okay, so this is something that we can do, or another thing that we can do is to penalize, okay, using this equation. Using this equation, I try to minimize the error and also minimize the complexity of the function. So I will get this lambda here, okay? And this is what we are doing here. In this case, the lambda is, in this case, this is ridge regression. That means that the thing that we are doing is to sum the parameters of the polynomial. Okay, the parameters of the polynomial means the coefficient of the polynomial that describes your data. Okay, so the idea is that, the complexity of the model is measured as the sum of the parameters or the coefficients of the polynomial. Okay, notice that if you have a polynomial of order 5, for instance, and the 3 first parameters are 0, okay, that means that you have a simpler model, in particular it would be a quadratic model. Okay? So reducing the numbers that you have in the parameters, okay, the idea is that these numbers that we have here are small. Okay, the thing that you're doing is summing all these parameters. And this is the complexity, and this is what we will use to penalize the function. Okay? So when I'm using a degree 25, I will penalize this polynomial of degree 25 that for which the sum of the terms is too large. Okay? And that's what we observe when we try on these different polynomials the training and test error. Okay? So you can see that we don't have this overfitting, okay, because we have limited the complexity of the model using this penalty term. Okay.
Another question. So
Yeah.
do we sum the coefficients or do we count the coefficients?
Yeah, you can do both things. Okay, they correspond to different criteria about the complexity of the model. But in this case, we are summing. In fact, we are summing the squared values of the parameters. In
So
this
we
case,
can have a 25th, like up to the 25th, or so to say,
yeah,
but it should be really small.
exactly. Yeah, that's the idea. Okay. Okay. Yeah.
Some question. In this case, actually using the regulation parameter is worsening the model, right?
Why worsening?
Because for degree 5, in the other one, the error is half there.
So in this case, what you have, you're avoiding for a polynomial of degree 25 to do weird things like this. Okay? Why? Because this polynomial that explains well the training data set has parameters that are very large. Okay? So in that way, penalizing this polynomial with this lambda parameter, because this polynomial has this term, has this term too large, okay, this polynomial will be discarded, and another polynomial of degree 25 will take control, will be the one that minimizes the regularized term.
But in the not regularized one, wouldn't we choose already a smaller degree?
So if I understand well you mean that in this case, this model is better than maybe this other model, even when the degrees is larger. Is that what you're saying?
No, I'm saying like in the other case, when it's not regularized,
Yeah.
the degree number 5 is already better than the other ones.
No, why did you say it's better? It's better from the point of view of the training error.
Not 25, degree 5.
Ah, yeah, degree 5. Yeah, but it's not here, the degree 5. If you plot degree 5, you will see that it fits better the data. It's something between this and this fitting of the data.
Yeah, so like if we have that, would we have to consider regularizing it, or would we be happy with it?
Yeah, you can do both things. You can try polynomials that are not regularized, and then you have to try the minimum of this function, and this is okay. Or you can try to regularize, okay? And in this case, you will find the best model, and that in this case maybe is degree 20 or whatever, okay? But regularize it, okay? And in this case, even that we have a degree that is larger, the model is simpler because we measure the complexity of the model by the sum of the parameters, and this is the one that we will choose. Okay, so you can do both things.
A follow-up question on the point, which is, if you do have like these limits on the parameter size, is it weighted by the power to which the parameter like is multiplied? So for example, is it simply the sum of the squares, or do we also enforce that it has to be like, for example, if it's degree 25, we also make it be extra small?
Usually we do this simple approximation that we have a measure of the complexity. The measure of the complexity is something like this, the sum of the parameters independent of the number of parameters that you have. Okay? And then this is the regularization parameter, that is a value that you have to find for your data. Okay? But usually we do simple things like this. We don't do some things that are complex like I don't know. With simpler things, the regularization works well, like usually. Okay. Okay. So yeah. So we will stop now this lecture. Remember the things, the important things that we have seen in this first set of slides. That this is about the data that has to be represented in a tabular form. The processing that we have to do, the different kinds of learning that we have, what the model is, the generalization, the different kinds of models that we have, what is the implicit here, the loss function, and the things that we want to minimize, that is the typical risk. The empirical risk is the thing that we want to minimize, and what makes us fitting, underfitting, and how we do regularization. Okay, that is a way to bias or solutions toward simple solutions. Okay, so let's stop here for 7 minutes, and later we will come back to the next.